Let's start section 2.3 with some ideas from sets. So I have this universal set which contains the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the universal set right here. And normally I would use set builder notation because I don't like writing out this many numbers. It seems kind of dull. We're going to use these a lot, so I thought we'd have them all listed right in front of us. Set A is everything in the circle on the Venn diagram, the circle A, and that's 1, 2, 3, 4, 8. Set B is basically the odd numbers from 1 to 10. Now, the complement of A, that's what this symbol means, the complement of A. It's everything that's in the universe. It's everything from 1 to 12, but not in A. So it's everything in the universe, get rid of 1, 2, 3, 4, 8. So we're left with 5, 6, 7, 9, 10, 11, 12. Try B complement. B is everything in the universe, that's 1 through 12, except for 1, 3, 5, 7, 9. So it's going to be 2, 4, 6, 8, 10, 11, 12. Now let's make it a step more difficult. This is A intersect B. That's a set that contains all the elements that are in both A and B, and from the picture it's 1 and 3. A union B is everything that's in one or the other. Well, what's everything in one or the other? 1, 2, 3, 4, 5, 7, 8, 9. There's no 6 in there. 1, 2, 3, 4, 5, 7, 8, 9. So there's 8 elements in there, and there's 4 elements outside of there. Now this is that A union B, but it's the complement of A union B. So it's everything that's in the universe, that's these 12 over here. It's everything in the universe that's not in A union B. And so that'll be the rest of them. That'll be 6, 10, 11, 12. So this notation, the complement of A union B, is everything that's outside of A union B, but still in the universe, and it's just those right there. This is the intersection of the complements. Now that's a little bit weird. That's weird enough that there's quite a bit of theory on this. So let's just take a look at it the slow way. The complement of A is everything outside of A. It's 5, 7, 9. I'm going to have to make this bigger. It's 5, 7, 9, 6, 10, 11, 12. And now we want to intersect that with the complement of B, which is 2, 4, 8. 2, 4, 8, 6, 10, 11, 12. And since we want the intersection, the 5, 7, 9 don't match the 2, 4, 8 in any way. The intersection of these two is 6, 10, 11, 12. So it seems as if these two sets are equal to each other. This set is equal to this one. So something about the complement of A union B and the intersection of A complement B complement, somehow they're the same. So if we write this out, if we thought there was a distributive property of this complement through the parentheses, we would think that this was true. And that is not true. But there is sort of a distributive property. You can kind of distribute the complement down, but then you have to put in that. So that's kind of weird stuff. So let's continue on. So right here, we're asked to find the intersection of the complement of A and B. So I have the complement of A right here, and B is right here, so we want to find the parts that are the elements that are in both. 1 is not, 3 is not, 5 is, 7 is, 9 is. So 5, 7, 9 are the intersection of these two sets. What is set subtraction? Well, set subtraction, you start with A, and you take away a few things from it. What do you take away from A? Anything that's in B. So you're starting with A, so I'm going to write down A just so we have it. But now in order to do the subtraction, we've got to take off any of the elements of A that are in B. So 1 is in B, so that one goes away. 3 is in B, that one goes away. And that's all that goes away. So A minus B equals the set 2, 4, 8. This last idea is surprisingly useful and surprisingly important in later sections, so I'd recommend that you understand it thoroughly, even though it might seem a little bit simple to you right now. So we can calculate the number of elements in A union B because our picture, our Venn diagram, tells us everything that's in A union B. It's all the stuff inside the circles, and we can count them. There's 1, 2, 3, 4, 5, 6, 7, 8. So this is 8, and that seems pretty simple. Now I'd like to ask a question. Does this happen to equal the number of elements in A, or the cardinality of A, plus the cardinality of B? Are these two equal? Will this equal 8? Well, there's a problem here. A lot of people think, yeah, stuff in A plus the number of things in B has to equal the number of things in the union. It seems clear to them. But watch what happens. How many things are in the circle A? There's 5 of them. How many things are in the circle B? There's 5 of them. 5 plus 5 is 10. 10 doesn't equal 8. What's happening here is really important. What's happening here is the numbers 1 and 3 that are in both A and B, that are in the intersection of A and B, they're being counted twice. The 1 and the 3 are being counted once when we count the elements in A, and the 1 and 3 are being counted again when we count the elements here. And if we want all the elements in A union B, we want them counted only once. So what happens if we take away the number of elements in A intersect B? Well, the intersection is 1, 3, and the number of elements there is 2, and this is true. 8 equals 10, take away 2. So we have a way of calculating the number of elements of a union of two sets. You add up the number of elements in each set, and then you subtract the number of elements in the intersection. And like I said, for such a kind of straightforward idea, you're counting some things twice, so you got to take away one copy of them, it turns out to be really, really useful in the immediate future.